Welcome to part 2 for section 12.5. We just have 3 problems to do and they won't take too long, but they're important and they will be helpful for your homework. So number 3, we are asked to find the equation of a plane that passes through 3 points. These are just random points. Again, I'm just going to draw a random plane and I will just throw my points on here, P, Q, and R. Okay? Now, these points are on the plane, and I could create directed line segments with them, and then we could think of those as being vectors that are parallel to our plane. So, for example, I could do something like from P to Q, and then from P to R. So I create 2 vectors that are parallel to my plane, and then technically, I could go ahead and find their cross product, and that would be a normal vector. Okay, so if I had PQ here and PR here, then my normal vector is going to be the cross product of PQ and PR. Okay, so that's the main idea there. That's how we're going to get our normal vector. We know we need a normal vector. We also need a point. Well, that's not hard. They gave us 3 points. You can choose whichever one you want. It doesn't matter. It'll still work out the same. And that's kind of the beauty of it. So first we'll handle the whole normal vector thing. So to find our normal vector, which is going to be PQ crossed with PR, first find PQ and PR. I'm going to call them something else, okay? I'm going to let A equal PQ. So when I create PQ, I take the Q values and subtract the P values. So it's 3 minus 1 in the first component, negative 1 minus 3 in the second component, 6 minus 2 in the third component. That gives me 2, negative 4, 4. B will be PR. I'm going to take the R points and subtract the P points. So it'll be 5 minus 1 in the first component, 2 minus 3 in the second component, 0 minus 2 in the third component, and that simplifies down to 4, negative 1, negative 2. Now, there comes a point where we want to be able to calculate our cross product a little bit faster, not because you have to, but because you actually kind of want to, because you calculate a lot. So I'm going to show you something. It's a little weird, but it works. So just kind of imagine an I hat and a J hat and a K hat up here. You can kind of see I've got my 3 rows, I, J, K, 2, negative 4, 4, and 4, negative 1, negative 2. So I should not have to necessarily set up a whole determinant because I can kind of visualize it here. So I could say that A cross B is going to equal I hat times the determinant with negative 4, 4, negative 1, negative 2, minus J hat. And now we've got the 2, 4, 4, negative 2, plus K hat. And now we have 2, negative 4, 4, negative 1. Working that out, I have an I hat, 8 plus 4, minus J hat, negative 4 minus 16, plus K hat, negative 2 plus 16. This works out to a vector with components 12, 20, and 14. All right, this is my normal vector. And then I'm going to let R naught, let me change colors here. I'm going to let R naught, I don't know. I'll just choose it to be Q. All right, so we'll be at 3, negative 1, 6. Again, you could choose P or R or Q. Doesn't matter. They all work. So now the vector equation of our line, or sorry, our plane, is the normal vector dotted with r minus r naught is equal to 0. We go ahead and plop those in. N has components 12, 20, and 14, dotted with r minus r naught. The components are going to be x minus x naught, which is 3, y minus y naught, which is a negative 1, z minus z naught, which is a 6, and that should all sum to 0. We go ahead and perform the dot product. We get 12 times x minus 3 plus 20 times y plus 1 plus 14 times z minus 6 is equal to 0. Go ahead and distribute. I mean, technically, yeah, 12x minus 36 plus 20y plus 20 plus 14z minus, that's 60, 84 is equal to 0. And then it looks like, so that's minus 16, that's going to be minus 100. When I simplify this, I have 12x plus 20y plus 14z is equal to, yeah, I think that's 100 when I move it over. And that is the equation of our plane. So again, we have quite a bit of work just to get to the point where we can write up our plane. And that's kind of what you need to be prepared to do on an evaluation in this section, okay? In this next one, we're not coming up with a plane, we're given a plane, and I want to walk through how we would sketch a plane, like what's the easiest way to sketch a plane. And I think back to 2D when we had to sketch a line. And the easiest way I always found to sketch a line was to graph the intercepts, the x-intercept and the y-intercept. And it turns out in 3D that that's like the only way you want to use to graph a plane, because we're not going to graph a huge collection of dots and form them into a plane. It's easier if we can just find intercepts and connect the dots, and we'll be good. So if I want the x-intercept, I'm going to let y equals z equals 0 in this equation. Then what happens is I just get 6x is equal to 15 and x is equal to 15 over 6, which is the same as 5/2. So I get an intercept at 5/2, 0, 0. The y-intercept, very similar, except I'm going to let x equals z equal 0. When that happens, we get an equation 5y is equal to 15, so y is equal to 3, and the intercept is 0, 3, 0. The z-intercept, we're going to let x equal y equal 0, and then we solve minus 3z is equal to 15, so z is equal to, it looks like a negative 5. So we have the intercept 0, 0, negative 5. So I have a negative z-intercept. That's fine. Go ahead and draw everything out. There's my z-axis, my x-axis, and my y-axis. I need to go down on my z-axis because I have a negative 5 intercept. Go ahead and get some tick marks for everybody. 1, 2, 3, 4, 5. Okay. Now, the x-intercept, the 5/2 is 2.5. So we're right here. The y-intercept is that y is 3. The z-intercept is that z is negative 5. And so I'm going to go ahead and connect these dots. And what I've drawn is the portion of the plane in the, looks like 5th octant. It doesn't always happen. Usually we're trying to aim for drawing the plane in the first octant, but of course, if you have negative intercepts, that's going to take you to a different octant. So just be aware of that. You can always kind of shift around your octant to how you need it, but Z going down just makes sense, so I'm not going to shift that. Okay, that's how we graph a plane. Find the intercepts, plot them, connect the dots. Remember, this is an infinite plane. It does extend through the first octant. It's just that when we draw a plane, it's impossible to give a picture of what it means to go on forever in all directions. Okay. Next one, and I think this is the last one. Determine whether the planes are parallel, perpendicular, or neither. And so we're given two planes. One of them is in standard form. And when it's in standard form, I can get information from it. This second one is not in standard form, so I'm going to move everything over to the right-hand side. I have 4x minus y minus 6z is equal to 0. Okay, now that's in standard form. Okay. In order to determine whether planes are parallel, perpendicular, or neither, we must determine if the normal vectors are parallel, perpendicular, or neither. If the normal vectors are parallel, then the planes are parallel. If the normal vectors are perpendicular, then the planes are perpendicular. If the normal vectors have no relationship, then neither do the planes, but we could find an angle in between them. So let's start with perpendicular and what we know. So we were told the other day that if two vectors have a dot product of 0, then planes, well, I should say the vectors are perpendicular, and so are the planes. So let's identify n1 and n2. n1 is going to be the coefficients in front of x, y, and z. So it has components 5, 2, and 3. n2 is going to be the vector with components that come from the coefficients of the second plane. So we'll call these 1 and 2. So n2 has components 4, -1, -6. So I'm going to go ahead and find n1 dot n2. So it's 5, 2, 3, dotted with 4, -1, -6. This is going to give me 20 minus 2 minus 18, which is equal to 0. Oh, I guess my work is done here. The planes are perpendicular. Because n1 and n2 are perpendicular. Now, just so you have it, if they had not been perpendicular, I would have moved on to check to see if they were parallel. And parallel vectors have a cross product that's equal to 0. So we have to remember these interesting geometric facts that we got out of the dot product and the cross product being 0 in order to allow us to run these tests and see if planes and lines are parallel and or perpendicular. That concludes 12.5. I hope it was helpful. Please reach out if you have any questions at all.